All right, thank you, Dr. Barden. Good day, everybody. It's great to have you here. Hopefully, I can walk you through this as painlessly as possible. Before we get started, I would like to thank again the graduate student who completed this work, Swagata Treya, who's now at Oregon State University. I believe he's actually on here as a guest. So, Swagata, if I say anything wrong, you can chime in and straighten us out. Uh, I'd also like to thank the other co-advisor, Dr. Eric McConnell, whose knowledge about the logging industry was very critical in getting our assumptions for the different models that we ran correct, uh, as well as Dr. Mohammed Marufazan and Bruno De Silva for helping in that modeling effort. If you attended last month, we did the first of three webinars. Uh, and in that webinar, Dr. Crosby walked us through setting most of the data up for the different mapping procedures and shape files and things like that. So if you're interested in the full suite of things, you'll need to go back and watch that video and look at all the supplementary materials. For today, we're going to focus on the modeling efforts that Dr. Mohammed Marufazan led, looking at particular optimization techniques and things like that. We do have additional materials for this webinar as well, including codes where you can go through and run the actual models that we ran with the data sets and things like that to see how we set everything up. It's not the entire suite of things that we've done. So if you're interested, once you go through those and play around with them, if you're interested in kind of going further down that rabbit hole to learn more, we can provide you with additional resources, as well as the thesis that Swagat worked on pretty tirelessly, which has a tremendous amount of detail, step-by-step processes that you could follow to repeat these procedures. So just a quick introduction here. If we're wondering kind of as a justification for the project, in the southern United States, timber harvesting, particularly in rural counties and cities, is vital. It's vital to the economic stability and viability of these regions. And as we well see, when a mill shuts down, a lot of times the town can lose upwards of 40 or 50% of its population as a result. Now, that's not just employment at the industry itself or the mill itself, but also the interlinkaged businesses in that economy as well. It also affects forest landowners. Roughly 89% of harvested wood in the United States comes from private lands. And if we look more in that green area that I've highlighted there, private lands account for about 58% of all timber removals in the entire country. This is very unique globally, in that private individuals would provide such a large portion. That doesn't mean that there's not a place for the public sector within this framework, and particularly with respect to infrastructure. That's what we're going to see today, how important that is in this process that's largely carried out between private actors, both at the mills and from the harvest sites themselves. So a little bit of background, we're looking at Mississippi specifically. The project was in part funded by the Mississippi Forestry Commission, and with their blessing, we were able to get these funds from a larger grant, which if you've watched the previous webinar, you can learn more about. But roughly 30 million tons of timber is moved in Mississippi annually, and that's the most recent estimate. It goes up a little bit, 2 or 3% most years, unless there's a big recession. But about 15 million of that is softwood saw logs, and softwood we're talking about, pine, typically in the southeast. It could be other species if you're in different parts of the country, but pine is the predominant one, and that creates lumber products that then go to your Lowe's and your Home Depot that people use for decking and framing houses and things like that. One reason there's been an interest in road and bridge infrastructure from the forest product sector and some of these public agencies that deal with forestry is within the last 5 to 7 years, uh, the sawmill capacity has increased, or announcements have been made that are going to create large increases in softwood sawmill capacity in all of North America, but particularly in the U.S. South, with uh, uh, I think about 50 to 60% of all of those increases coming just from a few of your southern states. And so, that part's really important. If we've already got road and bridge challenges that we face with respect to our existing mills, what is that going to look like if we add, uh, 15 sawmills in the southeast, and or the ones that already operate decide to increase their capacity by 20, 30, 40, 50%. And those numbers, those numbers that I just rattled off, that's what we're hearing from existing sawmills. And so if you've already got problems getting wood from harvest sites to your mill, those problems are about to get worse because the scale is about to grow. And again, back to my previous point about these rural areas depending so much on income and tax revenues generated by these mills and the forest supply chain in general. It's going to be an ever growing important topic that we have to deal with. When it comes to logging operations, about 40 to 45% of all of the costs just are just in transportation issues. And so, again, transportation involves carrying the wood from the harvest site to the mill. And so, again, as this increases in scale, if those costs increase, margins for the logging operators increase, it becomes harder to be a profitable business, and it can create up and downstream supply chain issues in that forest product sector. As I mentioned, in the South, forest economy is very, very important. And you can see from Mississippi, it's no different. If we were talking about the entire forest industry impact on Mississippi, I calculated the most recent numbers, and we're talking $12 billion. So these are just, farm gate values. If we include all of the interlinkaged businesses and economies, that number grows tremendously. So with that backdrop in mind, the objective here will be to investigate the impact of bridge weight limits on transportation costs for Mississippi forestry sector, particularly the softwood sawmill sector. There are quite a few other mills besides just sawmills in Mississippi and the surrounding southern states, but you kind of have to shrink the problem down to make it manageable initially, and then from there we can build it out and add industries as we so choose. Most transportation studies with respect to forestry do place emphasis on developing transportation cost minimization models, like what we're going to see here later. The point of the models is to facilitate resource allocation, optimal resource allocation, and route selection amongst available options. All with the purpose of getting, raw materials delivered from your initial harvest site to your mill. As a result, the application's increasing in the forestry sector, but as we'll see here, we haven't found anything in the literature that looks at how bridge infrastructure affects transportation costs in forestry, either in Mississippi or in the surrounding United States. And so there will be a lot of application we believe, for this research, in some way, shape, or form. There will be different issues in different parts of the country, but again, the title of the grant itself was one of the words in it was a blueprint, and that's what we intend for this to be. You can see the top bullet there. We've got a pretty crisis level issue when it comes to closed or posted bridges in Mississippi, with about 3,000 throughout the state. And we'll see a map here in a minute that really shows what the coverage of that is. It's quite profound. So to our methodology, again, our study area here, as you'll see, both on the the larger map there, and then the smaller one, we're looking at sawmills in Mississippi, but we had to include harvest sites that were outside of Mississippi because typically a sawmill has a procurement radius of 50 or so miles. That's the typical, it's a good round number. That's how far they're willing to go. Beyond that, there's going to be premiums that are going to have to be paid in order to move that wood accordingly. So what we did is we got data sets from the Forestry Commission and used some information from the RISI mill database to get volumes. So that gave us our mills, which you see there in the little white dots over on the right side there. And then our harvest sites, which we gleaned from the FIA database, or Forest Inventory Analysis. And that database shows harvested plots within a particular geography that you're examining. Going back many years, we just went back 10 years as a kind of an arbitrary rule. And that gives us an idea of the geographic dispersion of harvest sites for our softwood harvested products. So you can see there, I mean, those are the actual number of mills in Mississippi for softwood sawmilling. Those harvest sites, though, they're arbitrary in terms of they're only the ones that the Forest Service has documented. And, as I showed in that previous slide, we're talking 30 million tons of wood a year. There's far more harvest sites than those. Okay. So we had to do a little bit of a little bit of statistical manipulation in order to make those sites work. We didn't want to add sites arbitrarily, but we do need those sites to provide the wood to the mills. And so we did a few mathematical tricks in order to make that work, and we'll see those here shortly. So you can see just how widespread these posted and out closed bridges are, with the red being closed and the posted being the darker ones. I mean, it's pretty much a problem throughout the state, and you can see a little bit. It looks to be a little bit of a pattern over near the Delta, where there's more, there's more water. There's probably more rivers, or more. Not, well, there's certainly a river there, but there's more waterways, and so there's probably going to be more bridges generally. And those are also typically poorer regions of the state, and so these counties trying to come up with money to repair bridges, at least for the state, the local bridges, it's a big challenge for them. And so there is going to be a bit of an inequity with respect to this. The poor communities are going to be hit harder by this, which is all the more reason to try to address this problem, because you can, from a marginal perspective, you can improve people's lives the most in the worst places by addressing this issue. So you can see a number of the bridge data description over there in terms of closed and posted, to give you a little context of, okay, well, that's a lot, but out of how many, right? It's always, what's the denominator? So according to a 2022 National Bridge Inventory data from the Federal Highway Administration, 6.5% of bridges in Mississippi are structurally deficient. That's about 1,090. Another roughly 2,500 are posted or to lower weight limits. And if you also look at the Mississippi Department of Transportation's data set, they reported that out of about 5,800 state-maintained bridges, you're looking at close to 500-600 that are either closed or posted. So if you take the federal, the state, the local, and all those things and pack them together, that's what you're looking at in terms of closed posted that we were able to collect for Mississippi as of the most recent data available. So quite a daunting challenge in terms of just the sheer numbers. So we were able to get, as I mentioned, get that data on bridges from the Mississippi Department of Transportation, Mississippi Office of State Aid, Road Construction, and USDOT, U.S. Department of Transportation, Federal Highway Administration. So we had to, or Swagat did, he did the work here, had to put together a lot of different data sets in order to make all this stuff work. There are other routes, other than just county roads that from a from an optimization perspective, from just the math that the roads could be used. We need to know uh, all that coverage at all the different governmental levels just to have a better handle on things. And if you see over there to the right, this is really the most extreme case in our data set. And we'll see more on the statistics later. But you can see that harvest site, and this is right on the border of Louisiana and Mississippi. But you can see that blue route is the original route that from that harvest site to that nearby mill that truck could take. But because you have those two red dots right there at the corner, they can't use that route. That means that the actual truck is too heavy to go over those posted bridges, or if they're closed, and they have to reroute and take that red, that red line instead. And so it's quite a different path from harvest site to mill as a result. And again, I don't want to overshoot here. I did find the worst case just to drive home the point, but you can see how significant it looks there. So on to the data analysis. If we want to identify log trucking routes between harvest sites and softwood sawmills. And so, as the last presentation will show you and the related data, there's a whole process for getting all that data ready. And in order to actually find those shortest paths from the mill from the harvest sites to the mill, we use the Dijkstra algorithm. And again, you can read about that. We won't cover it in the presentation other than the name, but you can read about that more if you're interested. That's a very common algorithm to use for routing projects like what we've done here. And we had a cutoff distance of 57 miles. That was from Timber Mart South data that showed that's pretty much the critical limit for average loads to be hauled from harvest sites to mills. There are some that go further, of course. If prices, spot prices skyrocket, loggers would travel further because of the price at the mill's higher. But we're trying to get a nice average of things here. So 57 miles was our absolute cutoff. If there were no routes from the harvest site to a mill that were under 57, it would be kicked out. And so we did lose some observations as a result, which we'll see here in the next couple of slides. With respect to the supply chain modeling, we used a mixed integer linear programming model. And it's a fancy word for an optimization model that's used to solve decision-making problems. Again, our decision is how to get the wood from the harvest site to the mill the most quickly, where the objective is to minimize that linear function subject to constraints. But in this case, some of your variables are continuous, and some are integers, or they could be binary. And in the case for our model, the integer is the number of trucks. So you can't have partial trucks, right? You can't have 50 and a half trucks carrying wood. We have to keep that number as a whole. So it's one truck or two trucks, not 1.5 trucks, as it were. So that's where our mixed integer aspect comes in. And so the objective here: minimize the round wood costs along the shortest and alternate identified routes. So the shortest, and then if there's more than one, and then we also are going to add in that layer of, well, our shortest route is out. How much further is that alternate route that we've identified? So just some math calculations here. You can see, right, we're interested in transportation cost. And I put TTC there instead of what we had was TC. If you're an economist like me, TC means total cost. And so I had to put that acronym in there just for my own sake, so I wouldn't misspeak. But you can see how we've calculated the various costs that go into that overall transportation cost. The truck itself to travel from these sites to the mills, there are fixed costs associated with that. Things like overhead, insurance, purchasing, renting different items for equipment wise. And so once we have those costs and we know the amount that we're going to transport, we can get a total fixed cost for the entire entire environment that we're gonna calculate. You could do this at a smaller scale. It's just the geography that you choose, but we're going to look at state level impacts here. The variable costs are more complex and more interesting for the sake of our analysis. You could make arguments that the fixed cost dollars per ton, you know, that they would change. We've kept them constant in our model, except when we do sensitivity analysis. You could make quibbles about that, but they wouldn't change a whole lot in most cases. So we're trying to keep ceteris paribus here as much as we can to look at the variable cost changes. So you can see the equation there. Payload capacity is simply the maximum amount of weight that the vehicle can carry in addition to its empty weight, or what we call tare weight. And the number of truckloads just refers to the number of trucks required for transporting the saw logs from the sites to the sawmills. Again, we said anything over 50 miles, there's a hauling premium up to 57 miles. And so you can see how we've calculated that there, where you see distance under hauling premium. Again, anything past 57 would be chopped off. So that the largest that number can get is 57 miles. And then lastly, we have our fixed cost and our variable cost that go into those equations. They're actually calculated in Route Chaser. And Route Chaser is a software package produced by Mississippi State University. And Dr. Eric McConnell provided in our reference materials that should be available to you a video on how to utilize Route Chaser in order to come up with these costs. The great thing about having that is given different conditions or given scenario analyses that you want to run, you can alter those themselves before you implement them into an optimization model like we've done here. Oh, also I'd like to add variable cost. These are just costs that depend on distance. So fuel, maintenance, some labor, minor repairs. When we talk about maintenance, things like oil filters, changing the oil, wear and tear on tires, and those sorts of items. Well, in my head, I meant to go through those with the animation. Forgive me on that. You can see the decision variables here. So we have our sets for our optimization model. Sets are really, just think of it as different options. So there's harvest sites, there's mills, and they can use certain paths to get there. And however many sites and however many mills we have, and all the paths that can go amongst all those, that's how many sets are going to be available to run for the overall calculation. And so the sets are going to increase when we have our restrictions or our sites that are with the roads or excuse me, with the bridge outages or postings. You're actually going to increase the number of sets because there's now another option in place for you to utilize. You can see here the parameters that go into the model. We won't spend a lot of time on those. We've got some math that I want to show you in the next page so we can cover them a little more carefully. Let's see, penalty cost is an interesting one. So again, because we have a limited amount of harvest sites, we still have to fulfill the demand at the mill. If we don't, then a lot of times these optimization models they'll give you results that are not very practical because it's basically chosen to deal with the routing problem and not the mill demand problem as much. And so you can get some kind of wild answers. So in order to mitigate that, we have to make sure that demand gets filled, even if the harvest sites themselves can't get the wood where it needs to go. Okay. And you can read the thesis if you want to learn more about the amounts that we used and why we used those, but it's all based on previous literature that we were able to glean and inflation adjustments and things like that. So here you can see the objective function. We're going to try to minimize, right, the cost. So fixed cost, variable cost, and penalty cost. And the penalty cost, again, being any of unfilled demand times the price for the units that we're going to have to get from quote unquote somewhere else. Okay, so non-harvest sites. But we do know that the wood's out there, so that's not a really controversial piece of math to put in that equation. But the rest of that is just those different items that we looked at on the last page, subject to different restrictions, and they're very standard things. They're, we can't we're going to supply as much as the mill needs in terms of demand. We're not going to be able to, if we're going to supply as much as the harvest sites can. If they can't fulfill all of it, then there's going to be basically shadow supply in the form of our unmet demand. We have capacity restrictions so the trucks can't overload. Again, the optimization model, if you don't enforce that the truck can only carry so much weight over its tear, so it's roughly, I think, 84,000 pounds that the truck can carry, and the truck itself, has a certain weight, and then that allows you for, I think, another roughly 25 tons that you can carry in product. Then we can't let the truck go over that, because then it's not realistic. Otherwise, you'll have trucks that, we take one truck from the mill, from the harvest site to the mill, with 1 million tons on the truck, which of course is ludicrous. So again, I don't want to belabor this too much. We could spend a lot of time working through this, but the thesis itself has 10, 15 pages motivated by these different restrictions, the objective function, things like that you can explore a little more carefully. We're happy to answer questions about anything that you really is pressing you at the end of the presentation. But all in all, really just restrictions that are trying to get us to mimic reality as close as possible. So we end up here with two scenarios. First, here you can see scenario one, the derived shortest optimal routes permissible within the state's legal gross weight or vehicle weight. So again, as I said, the truck can't be over 84,000 pounds. That does change after July 1st of 2023. I think it goes up to 80. I think 88, but I'm not 100% sure on that. On the state highway with the purchase of a harvest permit. So again, all this assumes that the logger is able to get that in the first place. Again, here we don't have to account for any bridge weight limits. We're ignoring any restrictions that those might impose. And so we're only interested in finding the shortest real route from the harvest site to the mill. And then scenario two is the same thing, except now we're going to account for bridges that are either posted or closed that do not allow for that 84,000 pounds to go over the route that would be the most optimal one. Now it has to reroute, or possibility the truck has to decrease the amount of weight that it's carrying to meet that low bridge. We did allow the model that flexibility, and some people would say, well, that's not realistic because trucks won't underload. But in fact, if you look at the literature, the amount that we had from our study was around 2.77% that underloaded from the typical, I think, 25, 26 tons. But the Southwide averages are 5%. So even with the model specification that we made, we're still within that real level that is believable. Okay. So in the scenario two, we're gonna consider the bridge weight limits, and we're gonna utilize both that shortest and alternate route, and try to figure out what the difference is by having that in place. So how much more cost are we going to incur now that we have to go a longer distance due to those bridge obstructions? So once we pared down the routes, we had quite a few, but once we get down to the ones we could actually utilize, we were around 130 routes, 129 to be exact. And of those, we have about 30 that are affected by restricted bridges. Okay. Of those 30, 13 we were able to find alternate routes, and 17 we weren't able to find those. Now, that is in part a product of our 57-mile cap. So in the future to explore this more, we need to relax that a little bit. There were other reasons, just technical things that wouldn't allow us either. If they had an alternate route, the GIS program might have tried to route them on the interstate, but you can't carry the log trucks really aren't allowed on the interstate. If they're empty and they're driving back, that's fine. But you won't see, at least in Mississippi, you won't see log trucks on the interstate. And so if they only had interstate options, for instance, which in many cases these did, that was the only other option, then that route was just not available because the county would not give them a permit to carry on those roads. So the affected routes and the shortest optimal routes with restricted bridges along them. That's how we're defining that. We also had to chop out 2 sawmills because once we added these constraints, there weren't any feasible routes from the harvest sites to them. So we did lose a couple of sawmills in the process. Let's see, I think that's it for that. Yeah. So let's look further here. So we have our affected routes. That's our 30 there, right? And then we're going to pare that down again and look at the affected routes and then their alternative. So now this is what the distance was for those routes that we had identified that actually would have bridge problems associated with them. But if you could still go over the bridge, here's the distances you're looking at. But if you have to reroute, now you can see, the significant increases there in terms of the distance. Well, significant, depending on your perspective. I don't know if we did t-tests on this or not. I can't remember. But it is, it is a pretty noticeable jump in the overall distance for rerouting. And there's a lot of variation within that. Some were only a couple of miles. Some were, I think, into the teens and 20s. And so we've actually got a slide that shows that so we can see exactly, but quite a bit of variation. Yeah, here we go. So here's the shortest optimal distance with no obstructions. So you can see an average of about 31 miles. If they're forced to go on the alternate routes, then the average goes up to close to 36. And with the median, we're at about 29. And with the alternate routes, we're at 33.5. And so you can see that difference between the two, right? That's this purple line. So you can see what I mean by the amount of variation. I mean, this mill pair here, and that's that one I showed you earlier, right on the border of Louisiana. That's such a significant difference in terms of the added distance. So this is kind of another interesting component for individual sawmills. So depending on where you are, what county you're in as a sawmill, or counties that you're garnering most of your wood harvest from, you could be in big trouble in terms of what the loggers can bring to you at a profitable level. If it gets bad enough, loggers will quit working that route altogether. And so it isn't just a problem for our logging operators, although they feel it the worst. If the situation worsens enough, the mills themselves could face some sourcing problems, quite frankly. We haven't really seen that yet because there's just so much material available, at least in Mississippi. But things change quickly. And if we're going to add all this new capacity to the mill, there's going to be increased competition for harvest, for log trucks and wood harvesters as a result. Yeah, one last thing. So the additional distances, as I said, there were a couple of percent. So these went everywhere from 1.53 miles to 12.93 miles. And from in percentage terms, 3.5%. And that most this one up here, the most extreme one, was a 75% increase in trucking distance. So that's really a profound number. So here we're looking at the difference in minimum transportation costs between both scenarios. So we can see here That's our transportation cost per ton, that 835. The total transportation cost, so for the entire all the sites that we've included, all the mills, around 100 million. And you can see the corresponding variable cost, fixed cost, hauling premiums, things like that with it. And so if we go to scenario 2, we can see a noticeable increase in the transportation cost. Certainly, in terms of percentage changes, looking at the increase in total variable costs, we're at about 5.63 there. The hauling premiums, although small in number relative to the other two, percentage increase was quite profound, right? So this 0.08 million, it's about 11.5%. And then the number of truckloads required. So if there's more trucks, but it's the same amount of wood, that's going to be some trucks that are underloaded. So we've added about 3% the truck workforce that's carrying underweight truckloads to the mill. All right, so here we're looking at comparison of those total transportation costs per ton for each pair. So these are the HAs are the harvest sites, and the M is the mill. So those are our pairs, right? Our paths, the two that are carrying the wood there. And if we look at the additional transportation costs due to these restricted bridges, again, we got knocked down to only 13, so they're all accounted for there. You can see for HA 13 to M11 there, for instance, that's second to the farthest left, is around $2.19. If we look at the fourth from the left, HA 18 to M29, the increase of about $2.72 a ton. In HA 18 to MO, which is right in that, it's about fourth over. There's about $1.03 or $1.03 per ton, and so it just gives you a little bit of flavor of the additional costs. Those are the worst offenders in that particular scenario, but we're talking those numbers I mentioned. That's 40%, 25%, and a 10% increase, and that's you start to multiply that by a number of loads, that gets to be a pretty heavy burden on the logging operator. So that was our total transportation cost. If we look at some of the breakdown of the component parts here we're looking at variable cost, and you can see where those big blue spikes are. Those are the worst ones. We had percentage increases for the top three of an increase of 75%, 30%, and 15%. So again, even more profound in terms of the variable cost, because again, variable cost, part of it is a distance measure, and distances are increased. So we get that much larger variable cost increase due to the outages. So I think this is our last slide. Well, second to last. So we've looked at that. It was pretty straightforward analysis in terms of if you have outed bridges or posted bridges, then the trucks are they have to pare down a little. They can pare down a little bit, maybe their load, but you can't do that at scale. Underweighted trucks are over time, that's going to lose the logger money. I mean, it's just not an option to do for every load. And so what we wanted to look at was, well, which of these, if we increase them and decrease them, so for gross vehicle weight, our hauling premiums, our variable cost, and our fixed cost, if we increase and decrease those by 10%, both in scenario 1 with no obstructions, and then in scenario 2 with obstructions, how do things fare then? What do we see in terms of the variation in those overall costs if we change those little things by 10%, or the component parts by 10%? And maybe not surprisingly to some listening, is a surprise to me, because the first study I've done in this area, gross vehicle weight is by far and away the most important component. And that's interesting because there are many states that are toying with the idea of increasing the amount of overall weight that these trucks could be loaded with. In Mississippi, it's 84 currently. I think they're going to raise it to 88. There's other states that have said they're going to raise theirs, or they're considering raising it as a policy option. The problem is in Mississippi, and this is more of an anecdote, but when we spoke with people in some of the counties, we found that they were actually posting some of the bridges, even though the bridges had no significant deterioration on them. And the reason being is the county is responsible, the county government is responsible for fixing the bridges. Well, if we have to pay to fix them, let's just not use them, and then we don't have to pay for them. Well, again, this is not a tenable situation. So we're going to have to address that. You can't just sweep all your trash under the rug in your living room indefinitely, right? Eventually, you have to remove it, or you just have a big pile of trash under your rug in the living room. So interesting that the gross vehicle weight mattered so much, and you can see, interestingly enough, for the scenario 2, where there are the bridge outages or bridge problems, even increasing the gross vehicle weight doesn't buy you as much as it does when the roads are all in good repair. And so there's a bit of an additive effect. So increasing gross vehicle weight does help reduce costs in both scenarios, but with road obstructions, they actually mute the effect, right? So we've got a drop in 10% of total cost here, all right? If we drop that, or if we drop this gross vehicle weight, we're going to get this big response, but it's even bigger when we don't have road obstructions. And so we need to deal with the road obstruction problem in order to maximize any policy changes that would allow for more gross vehicle weight on the road. They're going to have to be in unison in order for it to have its most profound effect. Okay, so wrapping up here, I think we're at 42 minutes, so we're doing good. So main take-home point, gross vehicle weight had the greatest impact on the transportation cost. Variable cost was second. Fixed cost mattered. The premium obviously didn't matter, but again, it's small, but it doesn't look like it matters in comparison to those others. But it's also important to track that. If we have particularly long routes, then for the variation in that variable as it affects particular pathways is could be high, right? In our second scenario, again, we had about 2.77 additional trucks operating below this allowable gross vehicle weight. And so if this has the greatest impact on transportation costs, again, we don't want trucks underloaded. We want them loaded to their maximum, and we want that gross vehicle weight to be as high as possible. That's still, still meets safety requirements. So about 23% of the identified shortest optimal routes connecting sites to mills had restricted bridges on them. And many of those sites, if you'll look at the raw data that I sent you in the reference materials that Dr. Barden shared, you'll see, a lot of these sites, they're carrying wood to multiple mills, right? So the mill is receiving wood from more than just one harvest site. And so in that way, from the mill's perspective, it's even more pronounced. Around 37% of mills experience increased transportation costs due to the restricted bridges. Now, some people say, well, the mill doesn't actually pay that. That's fine. You can make that argument, but someone is paying. If there's increased costs for the logger, it's most likely the landowner that's going to pay. But over enough time, given poor enough conditions, the mill could find itself with a transportation issue in enticing trucks to its mill, given those increased costs. Because landowners, while there's a lot of them, so the logger can be a little bit picky. The landowner also can let their trees grow. They don't have to harvest. The logger has thin margins, so he or she does have to maintain a certain amount of wood flow from harvest sites to mills in order to meet payroll and to deal with maintenance costs and those sorts of things. So nobody really gets to say this is not my problem, as it were. If they do, that there could be some severe consequences for all parties. Restricted bridges led to about a 4% increase in transportation costs, amounting to about 34 cents per ton. So for the overall load, you went from about 835 to 869. And again, you think, oh, well, that's not too much. But once you start multiplying it by the amount of wood that gets transported and the number of trucks it takes to transport it, the number gets quite large, quite fast. As we've already mentioned, gross vehicle weight had the greatest impact on the transportation costs. So we do want to look at ways to increase that, but dealing with things like insurance and costs associated with variable activity, things that, also road conditions, right? We talked about tire replacements. If we have routed bridges, we could also have poor roads. That's more wear and tear on the log trucks. So those are also things that we can address to help mitigate some of these costs that the log transportator is dealing with. So some implications. So number one, assessing how restricted bridges impact hauling costs for logistics dependent sectors. It's kind of where we're at here, what we've described with this presentation here today. Identifying the most cost-effective log trucking routes. Again, if a mill knows that a county is dealing with some poor bridges, and that county is strapped for cash and can't repair them, that mill may want to be forward-looking and see what that's going to do to the overall cost for the loggers that supply them, and that's important because they need to make sure that wood is going to get to their mill so they can process it. And so there's a sawmilling, it should be an interest from sawmilling operations for this kind of work. And they can look at it from their perspective. They can retool what we've done here for their needs. From a larger perspective, so maybe Mississippi DOT, you can use the data that we've generated to do a priority ranking for maintenance and upgrades on closed and posted bridges, based on their impact on the local economy. Now, that part wasn't done here, but what we've done is a necessary component for calculating that number, looking at some sort of economic impact shock to the economy, given the conditions, the worsened conditions that the county faces. And you can get tax implications for that and all sorts of other things. That's important because the federal government, United States Department of Transportation does provide grants and things like that for infrastructure repair, specifically road and bridge. But one of the hiccups for that is they need evidence that there's going to be an improved economic outcome by repairing this bridge. And so more and more what you're going to see, I believe, is data like this being calculated. And one of the reasons why we wanted to do it was to kind of provide a framework for people to start crunching this data so that they can go to the U.S. Department of Transportation and have numbers that they can back up and show the impact of repairing a particular bridge or a combination of 4 or 5 or 6 bridges and so forth. Again, there were a lot of limitations as a blueprint. We really wanted to make sure we got the process correct. And so, there was an unavailability of posted weight limits on all posted bridges. We had quite a few that we just didn't know what their weight limits were. So we threw them out of the analysis, and there were a lot of them. And so that would potentially bias our results. I don't know which direction. But ultimately, it could be a problem in terms of trying to mimic reality as best we can. Again, if we're talking hundreds of millions of dollars in grants and things like that from the federal government. We want to get this part right. So we would need a little better information on those. And Mississippi DOT did speak with us about that, and they think that data can be gathered. So that's a good sign. The harvest sites, again, we only used the FIA subset, and that's a small number of the overall harvest sites that are actually out there. There's ways that we can deal with that statistically, but ultimately it's going to be difficult to know exactly how many harvest sites there were. You really have to get to a statistical distribution, and anytime you do that, you're introducing potential bias from the researcher as to what that distribution looks like. And so there's just not really a good way around that. We would like to try it with maybe 5-10 times as many harvest sites to then see. We dealt with it by having the unmet demand, kind of the shadow supply, but you don't get as good of a routing, an idea of the routing issues by doing that, because that wood then can come from anywhere if it's those shadow supply sites. Installing a limit of 57 miles likely eliminated pairs that would have exchanged wood, so we could try to flex that out a little bit. Again, you're always kind of balancing mathematical simplicity with the actual real world, reality. And, there are limits in terms of how well you can match those up. So future work, looking at developing models that also account for harvest and vehicle scheduling for more accurate estimation. What we're looking at here essentially are annual estimates, but turnaround times for trucks, how many trucks per day, looking at how weather changes affect these things. Those would give a lot of insight as well into kind of the day-to-day problems that these bridge outages and things like that could be causing. And lastly, taking the harvest and resource based data from different sources. Again, there are some things in Mississippi that can be utilized, but those aren't available in every state. And so again, it's going to be hard to make all of this uniform across states. Each state is going to have to leverage the resources that it has in terms of data in order to best tackle the problem and try to get a handle on, just how severe their bridge infrastructure problems are for not just the wood harvesting product sector, but other sectors as well that these bridges also affect. We have log trucks; those are semi trucks, but they're semi trucks carrying all kinds of items other than wood products, and so this is just kind of a partial analysis of a much larger problem. But at least we've got the methodology put together for how you can start to tackle that problem. All right. That's all I have. Does any one of there are other presenters have anything that they want to add? Anything I may have missed that they think is relevant before we adjourn? I think we have about 5 minutes.
Yeah, Sean, this is Eric. I'll just the law changed to 86,000 pounds
Okay.
on July 1st of 2023. So if they purchase a $25 harvest permit per truck, they can haul up to 86,000 pounds on state highways now.
Okay. Dr. Maroof, did anything in the modeling that you think was absolutely pressing that I didn't cover? It's kind of difficult to go too much depth, just given the time constraints. But
no, I think Dr. Shawn, you already covered all the major items. Thank you.
Okay, thanks. Yeah, here's a question: how transferable is the developed model to other regions or states with similar forestry supply chains and transportation infrastructure? Certainly in the Southeast, I think quite applicable. Again, like I mentioned, so when I was talking about different data that Mississippi had, so Mississippi has a very good database of what are called Section 16 harvests, and Section 16 lands are basically land that was given to the counties to raise money for school operations and school buildings and things like that. And so that data gives us locations as well as prices and things like that. And a lot of states don't share that data, or it's not readily available. It may be available with a FOIA request of some kind. I'm not sure how that works at the state level, but they may not have it at all. So that gives you some additional sites, which gives you a little more insight into where the real world harvest sites are. Alternatively, right, we considered in our study maybe just taking the existing harvest sites we had, because there's so much wood out there. As long as we overlaid a map that knocked out, non-timber areas. So we don't want to put a wood site or a harvest site where there's a city, for instance. So as long as we put a overlay on that, we could then generate randomly some sort of distribution based on the existing sites that we have, and then just increase those numbers until we got we thought was a good number of harvest sites that were realistic. We do know that harvest sites typically are 50 to 200 acres, but there's big tails on that data, in that some may be 2,000 to 5,000 acres, right? They could be these giant harvest sites, maybe not very many, but they do exist. And so, however you do that, if one researcher does it a particular way and another one does it a different way, and another, you're introducing variation across those states. And if all those states are competing for federal dollars, then there's games that people could play to make their state look worse, right? And so that statistical manipulation that you could utilize could actually, have some policy implications. And so that's where I see the problem. But in terms of the model itself, yeah, it'll work just as well, because FIA data is available throughout the 50 states. As long as you can get access to the mills and their demand and their locations, you could rerun it exactly the same. Right. We've got about 2 minutes. If you got any questions, you've got to speak now or forever hold your peace. All right. I think that's all. We'll see what we get back from the ones that watch the recording.
All right. Thank you very much, guys. Appreciate it. Folks, there will be another webinar in the series of 3 coming up in April. Check out the portal for dates and time. And we look forward to you joining us then. Thank you.
And the next webinar will be made available for the public. Is that correct?
Yes.
Okay.
Will be open to the public.
All right.
Thank you, Dr. Barden.
Yeah. Thank you all.